Hello friends. Welcome to our YouTube channel Engineers Revolution. In this video, we are going to learn some feeding techniques for microstrip antenna. Let's get started. The four most popular feed techniques used are the microstrip line, coaxial probe, both contacting schemes. Aperture coupling and proximity coupling, both non-contacting schemes. Let me explain what is contacting and non-contacting schemes. In the contacting method, the RF power is fed directly to the radiating patch using a connecting element such as a microstrip line. In the non-contacting scheme, electromagnetic field coupling is done to transfer power between the microstrip line and the radiating patch. Let's get into the techniques in detail. In this type of feed technique, a conducting strip is connected directly to the edge of the microstrip patch as shown. The conducting strip is smaller in width as compared to the patch. This kind of feed arrangement has the advantage that the feed can be etched on the same substrate to provide a planar structure. An inset cut can be incorporated into the patch, in order to obtain good impedance matching, without the need for any additional matching element. This is achieved by properly controlling the inset position. Hence this is an easy feeding technique, since it provides ease of fabrication and simplicity in modeling as well as impedance matching. The coaxial feed or probe feed is one of the most common techniques used for feeding microstrip patch antennas. As seen from figure, the inner conductor of the coaxial connector extends through the dielectric and is soldered to the radiating patch, while the outer conductor is connected to the ground plane. The main advantage of this type of feeding scheme is that the feed can be placed at any desired position inside the patch in order to obtain impedance matching. This feed method is easy to fabricate and has low spurious radiation effects. However, its major disadvantage is that it provides narrow bandwidth and is difficult to model since a hole has to be drilled into the substrate. Also, for thicker substrates the increased probe length makes the input impedance more inductive, leading to matching problems. By using a thick dielectric substrate to improve the bandwidth, the microstrip line feed and the coaxial feed suffer from numerous disadvantages such as spurious feed radiation and matching problem. The non-contacting feed techniques which have been discussed further, solve these problems. In aperture coupling as shown in figure, the radiating microstrip patch element is etched on the top of the antenna substrate, and the microstrip feed line is etched on the bottom of the feed substrate in order to obtain aperture coupling. The thickness and dielectric constants of these two substrates may thus be chosen independently, to optimize the distinct electrical functions of radiation and circuitry. The coupling aperture is usually centered under the patch, leading to lower cross-polarization due to symmetry of the configuration. The amount of coupling from the feed line to the patch is determined by the shape, size, and location of the aperture. Since the ground plane separates the patch and the feed line, spurious radiation is minimized. Generally, a high dielectric material is used for bottom substrate and a thick, low dielectric constant material is used for the top substrate to optimize radiation from the patch. This type of feeding technique can give very high bandwidth of about 21%. Also, the effect of spurious radiation is very less as compared to other feed techniques. The major disadvantage of this feed technique is that it is difficult to fabricate due to multiple layers, which also increases the antenna thickness. This proximity coupled type of feed technique is also called as the electromagnetic coupling scheme. As shown in figure 2, dielectric substrates are used such that the feed line is between the two substrates and the radiating patch is on top of the upper substrate. The main advantage of this feed technique is that it eliminates spurious feed radiation and provides very high bandwidth of about 13%. Due to increase in the electrical thickness of the microstrip patch antenna. This scheme also provides choices between two different dielectric media, one for the patch and one for the feed line to optimize the individual performances. The major disadvantage of this feed scheme is that it is difficult to fabricate because of the two dielectric layers that need proper alignment. Also, there is an increase in the overall thickness of the antenna. The rapid progress in wireless communications promises to make interactive voice, data, and video services available anytime and any place. Wireless communication systems come in a variety of different sizes ranging from small handheld devices to wireless local area networks. The desirable features of microstrip antennas, such as performance, flexibility, simplicity, high gain, and low fabrication cost, make them very popular for many applications. The slot in the radiating element gives a more compact design for the antenna and thus space, volume is saved. Since then these methods, aperture coupling and proximity coupling, have helped overcome several of the performance hindrances associated with direct contact excitation procedures. These include the inherent narrow bandwidth of direct contact fed patches and also the spurious radiation associated with the current discontinuity where the feed and the patch join. Despite overcoming these detrimental attributes, proximity-coupled patches have received little attention in the literature. This may be because the original form required an external impedance matching circuit to achieve a reasonable impedance bandwidth, approximately 13%. In a stacked proximity-coupled patch was developed that displayed a broad impedance bandwidth of approximately 25%, however this was achieved with the assistance of slots within the patch radiators. In wireless communication, much efforts has been devoted to reducing the size of microstrip antenna, with a lot of methods proposed recently, such as cutting slots on the patch, meandering the lateral edge of patch, using stacked patch, and adopting the substrate with high permittivity, etc. DGS is then used in the design of a proximity-coupled antenna for its miniaturization. The size of the developed antenna is about 68% smaller than that of the conventional one. Defected ground structure, DGS, is a convenient way to realize the slow wave effect. It has been widely used in the development of miniaturized antennas. Many DGS patterns are studied so as to improve their performance. More recently, many modified patterns, such as H, U, and T-shaped DGSs are presented for achieving high Q factor. Here in this video we found the results for individual antenna design, and then we go for the comparison of the results. Catch you in the next video. Stay tuned.